Let's talk about security risk conscious dynamic platoon formation using reinforcement learning. Given the growing interest and availability of autonomous vehicles, we want to make sure that the vehicles on our roads are safe to ride in and safe to be around. In this work, we explore the interactions between defenders and attackers using game theory and modeling. We created a game to model the case of a single vehicle under attack, which we then solve using the Minimax algorithm. We then created a multi-vehicle environment to simulate a platooning scenario, and we successfully trained an agent to act as the defender. Of course, all the source code for this work is open source and available on my GitHub. Starting with some background, vehicles have many components within them. Each of them has their own vulnerabilities constantly being discovered. Through compromising these systems, threats can be levied against the vehicle owners, manufacturers, the public, and the infrastructure. It's important to recognize the threats and to work out the ways that we can mitigate their impact. There are many ways to attack autonomous vehicles. Here we have two examples. The first is using a camouflage paint job to have the car be misclassified as a cake. The second is an example of an adversarial billboard that causes the steering model to try and drive the car off the road. Platooning is a way to save fuel by driving close together, which reduces drag. Interestingly, even the vehicle leader receives the benefits from this. A lot of research is going into making platooning viable for industrial trucking and for consumer applications. Reinforcement learning is the act of training an agent based on rewards from actions taken in an environment. The training process helps improve the decision-making policy so that the agent makes better and better decisions each iteration. Next, we'll look at the Minimax game we developed for single vehicle security. Here, we have a vehicle that contains n equals 8 vulnerabilities. It's a one-shot game where there are two players, the attacker and the defender. It's simultaneous play. Each player selects their action at the same time. In this game, the action is picking a subset of the vulnerabilities to attack or defend, constrained to a budget. In this case, each player can only have a total cost of 10. The attacker utility is calculated by summing the chance of success for the attacker times the severity of the vulnerability, modified by if the vulnerability was also chosen by the defender. In practice, brute force is enough to find the solution for games with around 15 vulnerabilities. We use insights from the Minimax game to help design the Platoon environment, which we'll look at next. In the Platoon environment, the agent is playing the role of the defender. It is responsible for moving vehicles in and out of the platoon, in addition to monitoring the vehicles. Similar to the Minimax game, each vehicle has multiple vulnerabilities with different severities. After each time step, the agent receives a reward equal to the size of the platoon. There is also a simulated attacker in the environment. Each time step, the attacker will choose a vehicle at random, which will use the hidden probability for each vulnerability to see if the attack was successful. If it was successful, the hidden probability gets set to 1, 0 otherwise. The environment will terminate if the sum of the severity times the hidden probability is greater than a threshold, in this case 5, for a single vehicle. Every other time step, the agent performs a monitoring action against the selected vehicle instead of moving it in or out of the platoon. This monitoring action copies the hidden probability into the observed probability, giving the defender more information to work with. Finally, there's an environmental behavior called cycling that occurs every other time step. The cycling action will choose a vehicle at random and will replace it with a new one, removing it from the platoon and changing the hidden probabilities. This simulates the dynamic population of vehicles that surrounds the platoon, since the vehicles are presumably leaving and joining the platoon throughout its lifetime. Here we have a visualization of the environment as it progresses. We start with no vehicles inside the platoon. Then after the first time step, the defender agent includes or selects the first vehicle, which is then included in the platoon. Additionally, another vehicle is cycled, and another vehicle is attacked by the attacker. In this case, the white text represents the hidden probability becoming 1, whereas the observed probability is still less than 1, because it hasn't been monitored yet. Then on the next step, the agent selects that vehicle to be monitored, and the observed probability becomes updated and shows 1 now. Then on the next time step, the defender chooses another vehicle to be included in the platoon, but at the same time, that vehicle was also cycled. And again, another vehicle is monitored, but in this case, there was no change since it hadn't been attacked yet. Then on the next step, another cycling action occurs, and another vehicle is brought into the platoon, which is also attacked. This continues on until 200 time steps, or until a vehicle has reached the total termination condition, where the sum of the compromised severities is greater than 5. And of course, the reward is equal to the size of the platoon. We divide so that the values are always between 1 and -1 because this helps the training algorithm. Next, we'll look at the training and evaluation. We trained with two different approaches, the first being deep queue networks and the second being proximal policy optimization. Each agent was trained for about an hour, and a third-party library named RayRLlib was very helpful for this process. We can see the results of the different policies after the training. So we can see that PPO and DQN both performed much better than the reference algorithms. So we have a random and a grow algorithm, which are designed to select random actions, and then the grow algorithm tries to make the platoon as large as possible. And then the no-op baseline algorithm doesn't take any actions. So of course the no-op lives the longest until the maximum length of the environment, whereas the PPO algorithm survives longer than the DQN algorithm, where DQN survives less long but has a larger average platoon size. So PPO has smaller platoons but survives for longer, giving it about the same reward as DQN. Whereas DQN is more aggressive with the platoon size, terminates earlier, but gets more rewards to balance it out. And of course, the grow algorithm has similar platoon size to the PPO algorithm, but it receives much less reward because of how aggressively it grows and then terminates because it isn't checking for vulnerabilities. And then the random algorithm also has an occasionally growing platoon. We can visualize the actions taken. This helps us see if there's any patterns in the data. So in this case, the grow algorithm always adds the vehicle at index 1 and rarely lives long enough to add the vehicle at index 10, whereas the no-op algorithm always takes the no-op action at index 0, and random has, of course, no discernible pattern in the behavior. In looking at the trained algorithms, they also have no discernible pattern in the data, which is good because the vehicles are randomly sampled. It wouldn't make sense for them to favor one of the vehicles or actions over the others, except for maybe the no-op action, which is index 0. And then there's also ethical considerations when working on this kind of system. Safety should not be the responsibility of individual members of society to keep paying for upgrades. And I personally wouldn't want to get hit by a car because the owner was unable to pay for extortionate software pricing. And airbags not included vehicles are not being sold, so it doesn't make sense for us to limit the availability of enhanced software for vehicle security, although this can be challenging when it starts requiring a lot of compute power for these new security systems. So if you do something like only allowing the highest security vehicles in the platoons, then that can limit the amount of people who can participate, and that means that cost savings from platooning can only be available to those who already have financial stability. So it's important to consider the impacts of using this technology. In our work, we make a lot of assumptions based on the way the environment operates, and there's plenty of opportunity for expanding this environment for future work, including having separate agents for the attacker rather than a static behavior. And you can also include this or expand this to include multiple platoons and costs for restructuring the platoons and having the order of the platoon members also be relevant, which can change the rewards that the agents would receive. Thank you.